Hello and welcome to Scully Unclassified. I'm Scully. I've been a software developer and architect for more than 20 years, and I created this channel to develop your skills as an embedded software engineer with focus on aerospace. On today's episode, we're going to answer a request for information, or RFI. This RFI comes from Ted. Thanks, Ted. And he'd like me to compare and contrast C++ programming, real-time C++ programming in a common OS, like Linux or Windows, and real-time C++ programming on a real-time operating system, or RTOS. Ted says, I've had plenty of experience with real-time programming, but never qualified for a real-time C++ position, because I never got exposed to the three items in my list up there, and I've always been curious how different it could be. Inquiring minds want to grow. Before we talk about programming languages and operating systems, I first wanted to talk about what real-time software needs to be. Real-time software needs to be fast, of course. It needs to be responsive to external stimuli. Like if you have a sensor that detects inertial motion, you want to be able to respond to that quickly, given your operating system and programming language. And most importantly, real-time software needs to be deterministic. You'll see a link above on my episode on GNC of how to actually fly a spaceship. That loop will take sensor information from an inertial measurement unit, run its algorithms, and then send out commands that'll control the thrust and maintain control of that rocket. That needs to be able to meet its time constraints of every time a new sensor reading comes in, how long does it have to issue commands out. A deterministic system, it'll always be the same time. The sensor data comes in, and so many milliseconds later, the command goes out. An average time isn't as important as how deterministic it is. You can have a really fast algorithm that runs fast on average, but if occasionally it goes over that limit, it's not acceptable because you're now missing your deadlines. You really need a deterministic system that's going to give the same repeatable performance throughout the mission. Before we talk about C++, let's talk about the C programming language. An excellent choice for real-time embedded systems, especially at smaller scales. What you'll hear most about the C programming language is that it's fast. That's generally true, but let's dig into a little of why it's fast. The problem that the C programming language was made to solve was to be able to write software to make an operating system, namely the Unix operating system. Different computer chips at the time had different program instructions, so if you're writing into assembly, you wouldn't be able to use that same assembly language program on different processing chips. So in comes the C programming language, gives a higher level of abstraction, but you can compile it then to work on different processors. What's important in terms of speed is that the C programming language is structured very much like the computer architecture. You have to worry about what your stack looks like. Do your variables go on the stack? You have to manage the heap yourself. There is no garbage collection. You allocate off the heap and give back to the heap, and there really is no protections for you. So a language that is more complex than C, or higher level you might say, will do a lot of checks. Can you get to the fifth element in an array if the array is only 3 pieces long? In the C programming language, it would just go to where the fifth one might be, and it may or may not crash. In a more complex or higher level language, it'll always check, but those constant checks, that constant help, does slow it down. So the C programming language is fast. Because of that, it doesn't help you, and it's very close to the architecture of the computer itself. The C programming language helps you write programs that tend to be very deterministic, in part because it doesn't give you much help. There's not a lot of layers of abstraction that makes it non-obvious what the code's doing and what might be slowing it down. One thing to keep in mind, though, as you write an embedded real-time C programming language, is that calls to malloc to allocate memory off the heap is not deterministic. So for example, you want to allocate memory. If you already have pages allocated to you from the operating system, it can be very fast. If you need to get more memory from the operating system, then that's going to take time. So each call allocating memory could take a widely different amount of time to return. That's why in embedded real-time programs, you'll often see pre-allocation of memory for your real-time threads, so they'll never have to have an indeterminate wait time getting more memory from the heap. So if C is so great, why would you use C++? And I'm sure there are many out there who say you don't use C for real-time embedded software. The reason why C++ is popular is because of the object-oriented constructs that let you modularize the software behind clearly defined interfaces, and then, especially on a large project, you have different teams or individuals working on those components. There's well-defined interfaces between them, and then it becomes easier to take the work of many different people and integrate them in a cohesive architecture. And C++ and object-oriented programming help with that. One of the big problems with C++ in real-time systems is that the standard library itself is not deterministic. Some of the help it gives you and the abstractions will go and allocate more memory off the heap, especially in the collections that are in the standard library. Real-time software needs to be fast, it needs to be responsive, and it needs to be deterministic. Let's take a look at Windows, Unix, and through its heritage Linux, and finally what real-time operating systems would do. Unix was designed so that many users could share the same hardware resources, so that you could have multiple processes, and say they were even the same priority, they would each get a time slice of the CPU, and you had protections in there so that you wouldn't starve out someone else's process, as multiple users would share the same piece of hardware. On a real-time operating system, the program that's being embedded in it needs direct access to its hardware, and needs direct access to those resources, and needs even deterministic access to them. So that if an interrupt were to fire, you have a thread waiting for that signal, and needs to deterministically wake up and being able to respond to that signal in a very predictable manner. I'd once written a piece of Windows software that, as an interrupt came in, it would signal a thread running at a very high priority, and it would go retrieve data from a buffer. And it worked great as long as the user didn't grab a window and start moving it around. As Windows was scheduling the tasks of what it needed to work on, it prioritized its user experience, because it was a workstation piece of software, above what its real-time thread needs would be. What's the difference between a process and a thread? Well, a process owns a virtual address space. And what that means is every process, apart from all the other processes sharing the system, have a set of memory addresses it can access in its virtual memory. That then goes to an MMU unit, actual hardware in the computer, that'll take that virtual address and translate it to a physical address, an actual place and physical memory on a RAM chip. Systems like Windows and Linux will also have swap files, so that if you have too many things loaded in memory, it'll take one of those blocks, it'll write it down to the hard disk, and then reuse that now physical RAM for a new virtual address. And as your program's running, it's all abstracted from you. You could see how this is a problem for real-time systems, because you want to make sure that as you access memory or dereference a pointer, you're not going to stop the operating system to go do disk I/O. That's just going to take too long. The POSIX real-time extensions for Unix and Linux give a memlock interface, so that you want to allocate everything you need off the heap, get all your memory set up, and then lock it into RAM. So as you're running real time, all your memory addresses, memory access will all take a deterministic and fast, short amount of time. You can also share memory between processes. So you can use library calls to map a block of memory into the virtual address space of many processes, and then use things like semaphores to synchronize their access. If you go back to the original Unix days, there was only processes and not threads. So every process had a single threaded control, or a program counter, of what instruction it was executing, and moved down as the program executed. When you bring in threads, now you have multiple threads of execution, multiple program counters going through their code, but they all share the same virtual memory space. So it's much easier to synchronize between them. You don't have to worry about mapping a block of memory from one process to another. All the threads within the same process all share the same memory, all share the same resources that have been allocated, and you have a new variety of synchronization mechanisms. For example, you can use mutexes that will deal with priority inversion. You can use condition variables that you can use to signal either one or multiple threads waking up when something happens. Some things you do need to worry about for thread synchronization, and even for process synchronization, especially in embedded real-time systems, looking at it needs to be fast, responsive, and deterministic. You want to try to avoid having threads that could be blocking on something, and maybe it is blocking waiting for a thing, and you have another thread waiting for it, and another thread in a circle and you've got a deadlock. So that you have two threads, each waiting on each other, but never will ever finish. Much like allocating all your memory before you get really running within your hard real-time applications, you also want to have all your threads spawned. Creating a thread is an expensive operation, and you want to create all your threads before you get running and before you start executing your threads that are important to your real-time goals. And you want to be able to, in the design, be able to predict their behavior. If you're spawning threads or losing count of how many threads you might have in the system, it's going to become harder for you to actually analyze what the threading behavior is going to be and make sure that your solution is fast, responsive, and deterministic. You want to avoid things like thread exhaustion, where you might have a thread pool and threads wake up, that thread gets assigned to wait on a particular resource, but you suddenly could have so many threads just waiting, you no longer have any threads left in your pool to handle incoming requests or incoming data. So you could get in the situation where you've allocated all your threads, but not enough. And then you have a thread starvation situation where nothing's running on the CPU because all your threads are waiting. And when you have that happening, you should consider asynchronous I/O. So instead of having a thread for every possible event that could happen, you can have asynchronous I/O that should tell the operating system to tell you that, okay, this particular resource is ready to be serviced. You'd have your thread available that could service multiple resources. Take that event as it happens, handle it as quickly as possible. Don't wait for anything else. Don't be blocking because you want deterministic performance. Have the thread handle that event, handle that job, and then go back as an open resource. And you can use asynchronous I/O to avoid having many threads all waiting on a particular, say, file handle or socket or sensor data coming in. Recent versions of VxWorks, a popular real-time operating system, now support RTPs, or real-time processes. So it allows you to separate those processes' address space so you can have one process trash the other one. Older versions of VxWorks and a lot of embedded software out there won't use processor threads. The idea is that you should have direct access to the operating system, direct access to the hardware, so instead they run tasks. They operate like threads, but in a way that there's only one process that runs on the machine. There's no protections from one task to another task, and also no protections from your code, from the user level code that you wrote, and the operating system itself. Being real-time and embedded doesn't stop you from crashing the operating system. In a modern application, I would recommend using those real-time processes so you get protection from trashing the memory of the operating system or trashing the memory of any other process. So real-time software needs to be fast, it needs to be responsive to external input, and it needs to be deterministic. C is a great choice for real-time embedded because it is organized the same way the computer architecture is, and it gives you very little abstraction between you and the computer itself. C++ provides an extra level of abstraction with its object-oriented design, allows you to create interfaces and have multiple teams execute the code behind them. That level of abstraction does come with some warnings though, as there's a lot of things in the standard library that are non-deterministic, often when they go and reach out to the heap to allocate extra memory. The main difference between real-time operating systems and non-real-time operating systems is things like non-real-time Linux. One of its first principles is to fairly share the resources of the computer amongst all its users and all its processes. In a real-time operating system, you want exclusive access, that you want deterministic interrupt handling, and you want to be able to take your processes and exclusively assign resources to them, whether it's locking memory into RAM or assigning a particular thread exclusive access to a processor core that's running on the computer itself. Thanks, Ted, for the question. I do appreciate it. I hope I answered it to some level of satisfaction. If you'd like to see more of these RFI episodes, I'd love to hear from you in the comments. Thanks for listening.